Imagine a bustling city where every inhabitant has a unique address that tells you exactly where they live. Now picture the universe of an atom, with electrons as the inhabitants. Each electron has a distinct address too. This address is what we call the electronic configuration. It's a map of where each electron resides in an atom. And just like knowing the layout of a city can help you understand how it functions, knowing the electronic configuration of an atom can give us insights into its behavior, reactivity, and how it bonds with other atoms. Atoms are like miniature solar systems. At the heart of the atom is the nucleus, a bustling hub of protons and neutrons. Orbiting this nucleus are the electrons moving in energy levels, or shells. These shells are like the different districts of our city, labeled as K, L, M, N, and so on, starting from the nucleus outward. The first shell, K, can house up to 2 electrons. The second shell, L, can accommodate up to 8, and so on. Now within these shells, we have smaller neighborhoods called subshells or orbitals. These are labeled as S, P, D, and F. The S orbital can fit up to 2 electrons, the P orbital up to 6, the D orbital up to 10, and the F orbital can hold an impressive 14 electrons. But how do these electrons decide where to live? Enter the Aufbau principle, the city planner of our atomic city. According to this principle, electrons fill up the lowest energy levels first, before moving to higher ones. This principle helps us determine the sequence in which electrons are arranged in an atom. And what about sharing space in the same orbital? Well, that's where Hund's rule comes in. It states that when filling orbitals within a subshell, electrons prefer to live alone in an orbital with the same spin before agreeing to pair up. We denote electronic configuration using a series of numbers and letters. For instance, oxygen, with an atomic number of 8, has an electronic configuration of 1s squared 2s squared 2p squared. This tells us that the 8 electrons of an oxygen atom are distributed among different orbitals. The periodic table, a chemist's best friend, organizes elements based on their atomic number and electronic configuration. Elements in the same group have similar outer electron configurations, leading to similar chemical properties. Understanding electronic configuration is like having a decoder ring for the mysteries of the atomic world. It helps predict chemical reactivity, bonding behavior, and the properties of elements. It's a fundamental concept in studying chemical reactions, molecular structure, and material science. So, why not take a whirl at writing electronic configurations for different elements? It's not just an academic exercise. It has real-world applications in fields as diverse as medicine, materials engineering, and environmental science. So dive into the world of atoms, explore their neighborhoods, and unravel their secrets. After all, in the universe of atoms, knowledge is power.